According to conventional analysis, insects generate only about 1/3 to 1/2 of the lift needed to carry their weight. Maybe you've read articles how the bumblebee is kind of this bulgy, flying insect, and he has these tiny little wings, and how can these little wings, lift up this bulbous body, right? And that was a problem. That was a mystery to scientists. That was worth looking into. How can these little wings support this weight of this bumblebee? Shown there in the picture. Scientists have come up with this fancy term now, right? The leading edge vortex, or the LEV, for those insiders who can use initials. Right? The LEV, the leading edge vortex, is also called controlled separated flow. Controlled separated flow is midway between streamlined, steady, laminar, flat flow of air, of some fluid, and unsteady, turbulent flow. It's between those two. Controlled separated flow. The airflow separates as sharp leading edges, which is why it's called a leading edge vortex, and the airflow, in this case we're using airflow, but it can work with water flow also. The flow closest to the object's surface is slower because friction with the surface slows it down. So as you get farther away from the object, the flow gets faster. All right? And that's called the boundary layer effect. So they say these leading edge vortexes, which are forming around the sharp edges of the wings, cause additional lift that we didn't know of before. In insects, LEVs generate the extra lift needed because the vortex stays stuck to the leading edge of the wing long enough for propagation, for it to be moving forward. Author Sarfati adds, insect wings have a very complex motion, rotating and changing the camber. These features require sophisticated programming from intelligent design. Now there's a debate here. Is it really additional lift? Some scientists are saying, well, because the wings are rotating around an axis and revolving around a point continuously, they're doing both. These little wings are rotating and revolving continuously. That motion actually enhances absence of stall. It doesn't stall out and fall to the ground. Absence of stall or additional lift. Which is it? I don't know why it couldn't be both, really. I'm not an entomologist. That's not my training by studying insects like this. But I would think there could be additional lift and also absence of stall built into the same system. He mentioned the term camber there. Anybody familiar with that word? I was familiar with it, but I had to look it up just to make sure. Camber is left to right angle displacement. Okay, left to right angle displacement is camber. And that differs from front to back angle displacement, which is called castor. So there's castor this way and camber this way. And then the inward and outward angle displacement is called toe, T-O-E. If you're working with three-dimensional motion, like airplanes in air or submarines in water, then you are probably more familiar with the terms pitch, yaw, and roll. Maybe you've heard those terms. Pitch, yaw, and roll. This is kind of similar to that. Okay, I told you Jonathan Sarfati was a pretty intelligent guy, so he's going to use terms like that maybe we're not familiar with.